Hello, I'm Lynn. I've decided to make explanation videos for Brain2Pix codes. I'm just going to walk through the different codes in this repository and then explain them so that those who want to apply Brain2Pix can understand the code better. And I will be splitting the videos in different parts. In this one, I will just focus on data pre-processing, specifically the targets only. And then in part 2 of data pre-processing, I will talk about the brain signals. So first, a quick overview of how the Brain2Pix method will look like. So training the Brain2Pix model consists of 2 main parts. The first part is mapping brain signals onto visual space to make these RFS images. And the second part is to use these RFS images to train a gun-like model that will reconstruct images that the subject has seen, so based on these RFS images. We're making use of the Doctor Who dataset, which can be found in this paper. You can click on data/code, and then if you click on this link, it will link you to the publicly available dataset. So we basically need a few things from this dataset. We need the Doctor Who movies, we need the brain signals, we need retinal topic mapping, and we need region of interest mask, which is all provided in this link. And then once we have all of these, we can start. Okay, so I'm going to clone the repository and get started. So once this is cloned, I'll open it in VS Code. So for the targets, we only need generate targets and warping targets. The targets need to first be downsampled spatially and temporally. In our case, we wanted to have 96 by 96 pixels per frame, and we wanted the temporal resolution to be matching the TRs of the fMRI data, which in our case is 0.7 seconds per frame. So this code basically does that and then converts the WebM files to NumPy files. Okay, target dir is the folder of all the Doctor Who frames. Raw dir is in addition to that path to point to the raw frames. We make new folders so that we can save it there later on. So this piece of code will take the raw data and then convert it to the desired dimensions, spatially and temporally. So what we wanted was 96 by 96 pixels. So if you want a larger frames, you should change it here, but we wanted 96 by 96. For the temporal resolution, we wanted it to match the 0.7 TRs that we have. So for the temporal resolution, we wanted it to be 0.7 seconds per frame, which is 1.4 frames per second. And then this code basically converts it and then saves it into this new directory called in-between processing. We do this for testing and training, and then load in everything and then save it as NumPy files. I'll open a Jupyter notebook to show how that looks. So here I have the code in the notebook format. So we first import all the packages, and then here you see the folder with the raw frames. This is the important code. Okay, because the training data is quite large, I'm just going to run the testing part. It's giving all this output. And this might take a while. And I'm basically saving here everything into NumPy. So 7 out of 7 means there are 7 runs. Everything is still happening in runs right now. Okay, let's see how this data looks like right now. So we want to look at the for example, run 1 frames. Then we just load the stuff that we saved. So see here, there, testing py, and then test video run. Wait, let's see something. And then let's say run number is 1 in this case, dot numpy. Okay, and then we have run 1 frames, which has a shape of this. This is the amount of frames per run. These are the correct pixel dimensions, and this is the color dimension. So we can visualize this by using matplotlib, and then we only want to visualize 1 frame. Yeah, so the data looks like this right now, and then we can look at a different frame. So this is how the target looks right now. So it's 96 by 96 pixels. And so the next thing we want to do is we want to apply a retinal warp, and also right now, and we want to combine the different frames in one file. So that's what happens here in the warping targets code. So we first want to load in the files, concatenate all the different runs, and then warp them. So this is the code that loads in the NumPy files that we made in the previous code, and then it concatenates all the runs together and warps the images with the Retinal warp. Let's see if it works. So basically all you have to do is you specify whether it's training or testing, and then it will generate the final targets. So obviously if you're using the code, you should change the directories to match the path where you saved your data. But other than that, if you are making use of the Doctor Who data, then you don't have to change anything else. All the runs get concatenated together to become one file, and every single frame of that file undergoes a retinal warp, and then it's saved here in this path. So yeah, basically that's what the function does. Images dot shape is this. These are all the runs combined. And if we want to visualize one of the images, we should select one of the frames and then just plot it. So as you can tell, this looks a bit different from the previous. This one hasn't undergone the retinal warp yet. The difference here is that it has the retinal warp, and it also saved in one file instead of separate runs. At this point, the targets are ready to go. So that was the first part of this tutorial. If you want a walkthrough of the brain signals code, then you should watch the second part. Thanks.